Hi there, welcome to another optimization video. So this video aims to improve my students' optimization skills, and it helps us just to understand the process a little bit better. It tends to be one of the most complicated things you learn in a calculus class as far as derivatives are concerned. So it's always a really good idea to make sure you practice this constantly, so that way you have a really good idea of the process, what the solution looks like, and how to get there. And the nice thing about a lot of these problems is that they tend to be really visual. So it is pretty easy to understand what we have to do in a problem and how to get the solution that they're asking us for. So let's read through the problem. I forgot something, forgot that little exponent. This should be square units. So if 1,200 square centimeters of material is available to make a box with a square base and an open top, find the largest possible volume of the box. So in every optimization problem, there are two quantities that we have to be concerned with. We have the constraint, which is a value that cannot change. And then the other quantity would be the thing that we are trying to optimize. So just as a quick reminder, optimization means to find the best possible outcome. And in strictly a calculus context, though, optimization refers to finding either an absolute maximum or an absolute minimum, which has many, many different applications, lots of different uses in various areas of the world. So let's draw a picture of the situation to help us understand it a little bit better. So we have a square base, and we have a fixed surface area, a fixed amount of material. So I want to draw what we call a neb of what the unfolded version of the box should look like. Should be something kind of like this. I might modify it a bit. Something kind of like that. The base is supposed to be a square, but I am really bad at drawing. This is definitely not a square. So just pretend like it's perfect, all right? Keep my self-esteem intact. So we want to create expressions not only for the volume, but also for the constraint. So we know that we have only 1,200 centimeters of material. So what that means is that this region right here, plus this region, plus this, plus this, plus this, they all have to have a combined total of 1,200 square centimeters. So let's create an expression. We're going to need to use some algebra to create an expression in order to ultimately use calculus to help us solve this problem. So let's see if we can create an expression for the area of all of these parts of the figure combined. So it's a square base. I'm going to call the dimensions of the square x. So that's x, and that's x as well. And then I want to use y to show the height of the box. So this is y. This is y. In fact, we're going to have every skinny rectangle is going to have dimensions that are x by y. In the square in the middle is going to have dimensions that are x by x, so x squared. Let's see if we can create an expression for the total perimeter. I keep saying perimeter when I mean surface area. I did that all the time in my last video. I get them mixed up for whatever reason. I don't know why. We want surface area. So I'm going to call SA surface area. In surface area, it's going to be the combined total of all of these sub areas. So it's going to be x squared plus 4 times whatever this is. So it's going to be plus 4xy. All right. We want to do something similar with the volume. We want to create an expression for the volume of the box. So volume is going to be the base times the height. So our volume expression is going to be x squared y. So now that we have both of those, we want to identify the constraint and the quantity that we want to optimize. So the constraint is going to be the value that cannot change, the thing that has to remain constant throughout the problem. So in this case, it would be the amount of material. We have a finite amount of material, so that's kind of a giveaway that this has to be the constraint. So the 1,200 centimeters surface area is going to be our constraint. Can I spell constraint? Yeah, I think that's right. And we have the quantity to be optimized. So like I said before, in optimization, in this class in particular, we are concerned with maximizing and minimizing things. If we reread the problem real quick, we're trying to find the largest possible volume of the box. So we want to maximize our volume. All right. So in general, whenever we have our information written clearly like this, we want to take the quantity that we're trying to optimize. Sorry, I can't talk tonight for whatever reason. Usually this doesn't happen, but we're trying to maximize our volume. And whenever we're trying to maximize or minimize something, we're going to need the derivative. The problem is, though, we have volume in terms of two variables. And in this class, we're not going to be differentiating multivariable functions. So we have to do whatever we need to do in order to put this in terms of just one single variable. And that's where the constraint comes in. We're going to use our constraint to put our volume expression, our volume equation, only in terms of one variable, either in terms of x or in terms of y. So I want to take the constraint. We know that it's equal to 1200. That's the amount of material we have available. I'm going to solve for y. So I'm going to start by subtracting both sides of the equation by x squared. So we get 4xy equals 1200 minus x squared. And then from there, all we need to do is divide everything by 4x on the left side and on the right. So we get y is equal to, we're going to have 1200 divided by 4x. That gets us 300 over x. Minus x squared over 4x. That's going to turn into minus x over 4. Whoops, x over 4. So actually, you know what? I think I might want to just keep it as a single fraction because it would be much easier to deal with just one fraction rather than two if we're going to be substituting it into the quantity that we want to optimize. Got a bit ahead of myself there. I jumped the gun. So what I'm going to do is I'm going to call this y, and y is just going to be 1200 minus x squared over 4x. So I want to take this y, I want to substitute it in for this y in our volume expression. So volume is going to be x squared times 1200 minus x squared over 4x. So we can simplify just a little bit. We can reduce the power of x in this outer factor. If we divide the top by x and divide the bottom by x, we're going to get x to the first on top. And then we're going to have just 4 in the bottom of this fraction. This x is going to be eliminated. So let's go ahead and distribute. We're going to get 12x squared minus x cubed over 4. And I'm going to be lazy to write this next part. So this is going to be 1200x minus x cubed over 4. So now that we have our volume expression in terms of just one variable, now we can find the derivative. We can find the derivative of v with respect to x. So v prime. So let's go ahead and maybe factor out the 1/4. It might make things just a little bit easier to work with. So instead of having all of this over 4, I'm going to write this as 1/4 times this expression. Just makes the busy work a little bit easier for us. I like easy in my math. I don't know about you, but I like things as easy as possible. I'm very lazy. So let's go ahead and take the derivative. We're going to have 1/4 times whatever the derivative is of everything in the parentheses. So this is going to be 1200 minus 3x squared when we take the derivative of x cubed. All right, so now that we have that, what we want to do now is find the critical values. And remember, the critical values are locations in the domain of a function that result either in discontinuity or a horizontal tangent line. In other words, the place where the derivative will be equal to 0. We want to identify all the x values that produce a 0 derivative. So we accomplish that by setting our derivative equal to 0. and then solving for x. So what I want to do is I want to multiply both sides of the equation by 4. That way this 1/4 goes away and we still have 0 on the other side. And then after I multiply both sides by 4, I'm going to add 3x squared to both sides of the equation. When I do that, I get 1200 equals positive 3x squared. So what I'm going to do now is I'm going to divide by 3, and then I'm going to take the square root of both sides. So 1200 divided by 3 is 400. I'm going to switch signs because of my OCD. 400 is equal to x squared. So x would be equal to the square root of 400, which is 20, actually plus minus 20 in this case. So now that we have two critical values, we want to test our work. Humans aren't perfect, especially not me. I make plenty of mistakes. So what I'm going to do is I'm going to test my work to verify that this actually does produce the result that we're looking for. I want to verify that it actually does produce the biggest possible volume given our constraint. So in some cases, we can use the second derivative test. We have some function, and if we take the second derivative of our quantity that we're trying to maximize, if we get a positive constant when we take the second derivative, it means the entire function would be concave up, which means we have a true local minimum. Otherwise, if we do things the other way, if we find that our second derivative is a negative constant, it means our function would be concave down on the entire interval, which means that we have a true absolute maximum. Unfortunately, I don't think that method would work very well in this situation. So what I'm going to do is I'm going to use a sign chart instead. This is something that I learned in my high school calc class when I took AP Calc in high school. And this is our default method. We never really used the second derivative test in my high school class. We always just defaulted to the sign chart. So we're using our sign chart to compare values for v prime, depending on x. So let's put on our critical point first. So first of all, we have x is minus 20 and x is positive 20. We know that x can't be minus 20 because if we look at our picture, it just does not make intuitive sense whatsoever to have a negative value for x. We can't have a negative distance, at least not on any rulers I've seen. So we're going to discard the negative 20. We're going to accept only a value of positive 20. This is the only critical value that we can use. It's the only non-extraneous solution. So we start by putting the critical value on a number line. And I put a 0 there just to show that we have a 0 when we plug in 20 into our derivative. Now the trick is to pick a value that's less than 20, and then also pick a value that's greater than 20. And plug both of those into the derivative. It'll tell us the intervals on which our function is increasing and decreasing. So I am extremely lazy. I'm going to just plug in 0. V prime of 0. So we're going to have 1200 minus 0 on the inside. We're going to have 1/4 1200 minus 0. When we do that, we get 300. And to be honest, we don't care about the actual value. The only thing we really care about is if it's positive or negative. We get positive 300. So what I'm going to do is I'm going to put a big plus sign to show that our function is increasing on this entire interval until we get to 20. So I want to pick a value that's greater than 20. 21 might be a good one, but the math gets really tedious when you're trying to grind through big numbers like that. So what I'm going to do instead is I'm actually going to theoretically take an infinitely large value of x. So I'm going to ask myself theoretically what would happen if we plug in infinity into our function. In other words, I'm going to take the limit as x tends to infinity. Not of the function itself, but of the derivative of our function. Limit as x approaches infinity of this expression. So the only thing that has a variable term, the only thing that has a variable factor would be this term right here at the end includes an x. So theoretically, if x were to get ever so large, if x were to theoretically reach infinity, we would have a negative number. We would have 1200 minus a mind-bogglingly huge number would produce a negative. And because the limit gets us a negative answer, the entire interval is going to have a negative derivative, which means the entire function is going to be decreasing absolutely anywhere where x is greater than 20. So let's talk about what this means real quick. So our derivative is positive, which means our function is going to be increasing more and more and more until we reach our critical value. We have a zero derivative, we have a horizontal tangent line, and then from there, it's going to be decreasing down, down, further, further, and further. So what that means is that we really do have a global maximum, which is what we want. We want to find the largest possible volume of the box. And this sign chart is actually what helps us to verify that this really does produce the largest volume. We can't alter this in any way, because if we have an x value that differs from 20 even slightly, we don't have the true maximum. So x absolutely must be 20 if we want to have the largest possible volume. So now that we have x, we need to find the y value that goes along with that. So what we can do is we can take our constraint equation, we can plug in our x value and solve for y. So x is equal to 20. I'm going to take the constraint, x squared plus 4 times x times y is 1200. So I'm going to go ahead and plug in our x value. X is 20. So 20 times 20 is 400. I'm going to subtract 400 on both sides of the equation. So we have 4 times 20 times y, which gets us 80y, equals 1200 minus 400, which is 800. So if we divide both sides by 80, we get y is equal to 10. So we have x is equal to 20 centimeters. And we have y is equal to 10 centimeters. And these are the dimensions needed to produce the absolute largest volume of our box.